Hi everyone. In this video I'm going to take you through my autocomplete implementation for large-scale systems. And this system would be something that would be used to support these suggestions, for example. So you see that as I type here, you see a list of suggestions. So the system would not only provide them, but also build them on a very large scale, like here in Google search, for example. Now, bear in mind that this is my interpretation of the problem, and there are many ways to approach this. And that being said, the first thing that we have to do is visit this repository on GitHub. You can find the link in the description below and clone it. While this is cloning, let me just say that there is a blog post going through all the details of this system, and I'll post a link in the description below as well. Now we enter the created folder, and the first thing that we have to do is to run the system. So we do this make run, and this make task deploys the system via Docker Compose, as we can see here. It commands some services to have multiple instances, like this distributor front-end service, for example. And to make it clearer, this front-end, back-end, and collector service will have multiple instances here in this implementation. Now that the system is running, let's create the Basilar Zookeeper nodes and HDFS folders by running this make task. As we can see here, these Z nodes and HDFS folders will be created by this task. We can see the created HDFS folders by visiting the localhost at port 9870 in our browser, and then go to browse the file system. The created folders are here. All of these folders are empty, like this one, and we'll come back to this later. We can also see the created Z nodes by running the Zookeeper client shell on the Zookeeper instance with this command. From here we can explore the created nodes like this, for example. Now the system is running and has the basic structure in place, but it doesn't have any data that it can build upon. So let's populate the system with some example searches by running this populate search task. This will send a collection of example searches to the system like ball, bank, car, etc. What this is doing is feeding these searches to the assembler. The assembler will collect and process all of these search phrases, and it's going to eventually build a data structure that the distributor can use to efficiently provide these autocomplete suggestions that we've seen before to any client that asks for it. In detail, we are feeding a series of searches to the search endpoint, and since the actual searches are outside the scope of this implementation, we're just going to directly send the query to the assembler's load balancer, which in turn sends it to one of the collector backends, and the collector backends send them to the phrases topic in Kafka, the message broker. As these messages arrive in the message broker, they are then pulled out and dumped into the HDFS file system. It's not shown here, but the service that performs this task is Kafka Connect. And if we visit this HDFS folder, we can see that it was filled out by Kafka Connect. And this is where the phrases are dumped. All of these are batched in 30-minute Windows folders. We'll see why this is important later. Now let's run the MapReduce jobs that will aggregate and rank the search phrases by running this command. This will trigger a series of MapReduce jobs. The first jobs will go through the most recent K folders and apply base weights to the phrases inside them, and the most recent folders will get the larger base weights. In our case, we'll only have one folder, but imagine that the system was running for some time now, and we would have several of these folders, and the phrases inside this one would be of base weight of 1, for example. The folder coming 30 minutes after would be of a base weight of 10, for example, and so on and so forth. Apart from applying base weights, we also do some aggregation of the repeated phrases by summing up their base weights. And the result of all of this is placed on this folder. From here, the next job merges all the different reduced results by further summing up the weights in the repeated phrases, and places this result in this folder. At this point, we now have all the weights by phrases summed up. The final job takes these and orders the phrases by weight, and we end up with a single HDFS file with the phrases ordered by weight. When all the jobs are completed, we also signal Zookeeper on a specific Z node that we just built this. To be more specific, if we visit this script, we can see the sequence of commands that we just went through. For example, this is the Z node that is used to signal that this series of MapReduce jobs were just completed. Now that we have built this list of top phrases, the try builder service notices that the Z node that we saw previously had changed. So this service builds a series of tries based on a partitioning scheme in order not to have one huge try, and places these tries on this folder. With a strategy similar to the one before, we use the zookeeper node to signal that the tries were built, and the standby backend nodes pick up this change and start loading these tries into memory from HDFS. Each backend service loads only one try, so each backend service is responsible for one partition only, and we can have more than one backend service for each partition for redundancy. When a given amount of standby backend services have their try loaded into memory, the try backend applier service notices this, and in one go swaps the active with the standby backend services by changing the zookeeper node that defines the current active group. We now have the system ready to provide us with the most recent suggestions for a given prefix. To actually see it working, we just have to visit localhost on our browser. And as we type a query, we can start seeing the suggestions popping up. And when we perform a search, we are providing yet another phrase for our system to process later. And if we run the do MapReduce tasks again, after doing some searches, we will eventually get the most up-to-date suggestions based on these recent searches as well. So, how does this web page actually get the top suggestions? As we type our query in the web page, it actually calls the top phrases endpoint, which in turn hits one of the front-end services via the load balancer, and this front-end will get the list of top suggestions by asking the appropriate active backend, which is listed in Zookeeper. Also, if this list of top phrases is cached in the distributed cache, which is Redis in this case, then the front-end service just returns it from there directly, instead of using the backend nodes. Bear in mind though that the distributed cache is disabled by default in this implementation, so that it is clearer what is actually happening here, but you can enable it in the Docker Compose YAML file. There are more details in the blog post on how to do this. And that wraps it up. Please let me know your thoughts about this implementation, and I hope this was useful.